In this video, I'm going to look at Descartes' Rule of Signs to show you how to use this theorem to find the possible real zeros of a polynomial, or in some cases you might want to find the possible solutions of a polynomial equation. So let's look at what the theorem states. Let f denote a polynomial function written in standard form. Okay, so that means it's going to be in descending powers. And then it states a number of positive real zeros of f of x either equals the number of variations in sign of the non-zero coefficients of f of x, or else equals that number less than an even integer. Okay, so you're going to be counting the number of variations of the expression, the polynomial expression, generally from left to right. Okay, and remember this is going to give you possibilities, the possible zeros. The next statement states the number of negative real zeros of f of x either equals the number of variations in the sign of the non-zero coefficients of f of minus x. Okay, so in other words, you evaluate the polynomial at minus x and then you look at the variations from that result. Okay, or else equals that number less an even integer. Okay, so before I look at some details of that or examples, here's your polynomial f of x. The exponents n minus 1, n minus 2, those have to be non-negative, and here we're looking at where the coefficients a sub n minus 1 and so on are real. So that's the polynomial equation. If I set that equal to 0, that's a polynomial. If I set that equal to 0, then I have an equation. So just a quick example here. If I have y equal to, say, x squared minus x minus 12, and instead of y, I could use p of x for polynomial, or I could just use f of x. Okay, that's not that important. Okay, so that's your polynomial second degree, and then of course you have your polynomial equation. If I just simply set that equal to 0, x squared minus x minus 12. Okay, so the zeros of this polynomial, which of course will correspond to where the graph crosses the x-axis, are going to turn out to be the solutions of this equation. So this has to be equal to 0. Okay, so there you have it. Okay, so let me clear this. And let's look at what we have here. Okay, so this one states, discuss the real zeros of the following polynomial functions. Discuss the real zeros of the following polynomial functions. Okay, so the first thing I'm going to say here is this is third degree. We look at that. We look at the highest degree term here. It's in descending powers. So this is degree 3. So this is a third degree polynomial. So you would expect to have 3 zeros. Remember, a polynomial can have real zeros, or it can have non-real or imaginary zeros. Imaginary zeros will look something like a plus bi. Okay. Okay. So you could have a zero, say 1 plus 2i. These are imaginary zeros. 1 minus 2i. Okay. So you can have real zeros, you can have imaginary zeros for polynomials. Okay, delete this. Again, this particular video is not to show you how to solve these, because I do have some videos on that. This is just to apply Descartes' Rule of Signs. So here we're discussing the real zeros. So since it's degree 3, we expect to have at most 3 zeros. Okay, at most 3 zeros. So we could have 3 real zeros. We could have, say, 1 0 and then 2 imaginary. The thing you have to keep in mind that is the imaginary zeros always come in pairs. So if I is a 0 an imaginary zero or non-real zero of a polynomial, then minus I also has to be. They have to come in pair, conjugate. So A plus BI and A minus BI are conjugates. Okay. Okay. So as far as discussing the zeros, we expect at most 3 zeros, but it could be a combination of real and non-real. But in this case, we're looking in particular at what real zeros does it have? What positive or negative real zeros does it have? So we count the variations in sign. So again, what the theorem is telling you is count the variations. So as an example, let's say we got 8 variations in sign, counting these signs from left to right here. Okay. And let's see what this said. Okay, so notice, if you have it written in standard form, the number of positive real zeros of f of x either equals the number of variations in sign of the non-zero coefficients of f of x, or else equals that number less an even integer. Okay. So let's look at this. So let's say we got 8 variations. Okay, so let's look at all the numbers that are less than 8 by an even number. Well, that would be, say, 6, 4, 2, and 0. Right? You take the difference of 8 between 8 and 6, 8 and 4, 8 and 2, 8 and 0, you get an even value. Okay. So remember, this is actually counting the zeros. So I can't go negative on this. Okay. So let's say you had 5 variations in sign. Okay. Let's get the number less than 5 by an even integer. So that'd be, say, 3, right? The difference is 2. The next one would be 1, because the difference between 5 and 1 is 4. Now if I subtract, I can't go any further because then I get a negative. Okay. So I stop right there. If I have, say, 4 variations in sign, okay, the next value would be 2. The next value would be 0. See, the difference between any of these is from 4 minus 2 is even, 4 minus 0 is even, and then I stop at 0. So basically you're just subtracting 2 is what you're doing. Once you count the variations, simply subtract 2, keep subtracting 2, but you don't want to get to a negative value. So you're either going to stop, say, at 0 or stop at 1. Okay, so now hopefully that's clear. And you do the same thing. You do the same thing if you're counting the negative zeros, except you evaluate the polynomial at minus x, and then you do the same thing. Okay, and I'll show you in the example here. Okay, so for this one here, we count the variation. So again, remember, this has to be in standard form. Okay, so you want the highest degree descending power, so it's x to the third, and then the next term minus 2x squared, and then an x, and then the constant. Okay, so again, every time it changes from plus to minus or minus to plus, it's a variation. So notice here it changes, so that's 1. Here it changes again from minus to plus, that's 2, and then it changes to negative, that's 3. So we have 3 variations. 3 variations. So that means that I can have 3, subtract 2 from that, that's 1, and I can't subtract 2 from 1 because then I get a negative. And remember, this is counting, so this is saying the number of zeros, so I can't say negative so zeros. Okay, it has to be a positive or 0. So subtract 1. So this one then has 3 or 1 positive. Real zeros. Okay. So again, these are possibilities. So this is simply saying it could have 3 positive real zeros, or it could have 1. You don't really know until you find them. Okay. Now, for the negative ones, we have to find f of minus x. Okay, f of minus x. What is f of minus x? Okay, so replace the x by a minus x. Okay, so if I put it in the first term there, that's going to become a negative, right? The coefficient will become negative. If I put a minus x in the second term, because of the square, it's going to cancel this negative, and this is going to stay negative. Okay, and if I put it in for x, that becomes minus. So I'm just looking at the sign of the coefficient. Okay, and then the last term stays negative. Okay, so how many variations in sign do we have? It stays negative, so I have 0 variations. Okay, so this basically tells me that I have 0 or no negative. Real zeros. Okay, so if you were to solve this by techniques covered in some of my videos or in your classes, you would find that the zeros would be either 3 or 1 positive, no negative, real zeros. Remember, the degree is 3. The degree is 3, so you expect to have 3 zeros total. So like I said, you could have a combination of real zeros and non-real zeros, or imaginary zeros. So just to show you, in this particular case, if you were to solve this equation using standard techniques, you would find that the zeros for this polynomial are 2, I, and negative I. Okay, so what does it turn out then? It turns out that this one is the actual one right here. Again, the Descartes Rule of Signs, the theorem only gives you possibilities. So it's 3 or 1. Well, it turns out that in this case it's 1 positive real 0 and no negative real 0. Okay. Clear this? Go to the next one. Okay, this one is again in standard form. You have the highest degree term, then the next one, and so on. So degree 4. So it has degree 4. So what type of zeros do we expect? We expect at most 4 zeros. Okay, it could be that they're all real zeros. It could be that there's a combination of real zeros and non-real zeros, but the total has to be 4. Okay, and you could have a repetition. Okay, we could have 4. Say 2 could be a 0 multiplicity 4. It could be repeated. Okay, so first let's find the possible positive real zeros. Okay, so let's count. It's in standard form, so count the number of variations. So go 1, 2. Okay, 2 variations in sign. 2 variations in sign. Okay, so that means I can have 2. Okay, and then I subtract 2 from that. So this, I'll say 2 or 0 positive real zeros. Okay, so I could have 2 positive, or I could have none. Now let's look at f of minus x. Okay, so all I'm doing here is just replacing the x by minus x. But notice, because of the even powers on the first 2 terms, those signs are going to stay the same. So this one, if I replace the x by minus x, the first term is still going to stay with a positive coefficient. The second one will stay with a negative coefficient, and of course the last term, doesn't have an x, so it's going to stay positive. Okay, so again, count the number of variations, plus to minus, and then minus to plus, so there's 1 and there's 2. So again, I can have 2 or 0 negative real zeros. Okay. Now, if you actually try to solve this, find by trial and errors, find a 0 and then factor it. For example, you can see easily here that if I put a 1 where the x is, the first term becomes a 1, the second term becomes a -5, 1 minus 5 is a -4, and 4 gives me 0. So I know that 1 is a 0, and I can go ahead and find some other values and eventually factor this out. Okay. But anyway, if you actually solve this, you're going to find that the zeros of this polynomial are 1, -1, 2, and -2. Okay, so these are the possibilities that the theorem gave you. So what was the actual answer? Well, if you look at the solutions I gave you there, it's actually 2 positive and 2 negative. Okay. Now keep in mind, you could do the same sort of thing if these were equations. So if I just remove the f of x and set this equal to 0, then they were looking at possible solutions to the equation. But the technique is going to be the same. You know, as soon as you get 1 or 2 zeros, you can start using synthetic division and factoring it and finding the rest of them. Okay. Go to the next one. So notice on this one, it's in descending powers already. X to the 8th, 2x to the 6th, plus x to the 4th, plus 2x squared, plus 9. But notice, all the signs are positive. So I have 0 variations. Okay. So notice in this particular case, I can't subtract 2 because I get a negative. So all I can do here is say I have 0 positive real zeros. Or if you want, I have no real zeros. Now notice, to find the negatives, the possible negative zeros, real zeros, I replace the x by minus x. Okay. But again, because all the powers are even on the x, when I put a minus x in there, and the last term doesn't have an x, so I was going to say positive, there's no variation. The signs stay the same. So there's 0 variations in sign for f of minus x also. So this one, then you would say you have 0 negative real zeros, or we have no real zeros. Okay, so we know we have degree 8 for this one. So degree 8 tells me that I can expect at most 8 zeros, and it could be a combination of real zeros and non-real zeros. Okay, some negative, some positive for the real zeros, and so forth. Well, in this case, though, using Descartes Rule of Signs, we know for sure there are 0 positive real zeros. There are 0 negative real zeros. Okay? So remember, real numbers are the only ones that have a sign, positive, negative. Complex or non-real zeros, there's no sign associated with them. Okay? So this tells me that, okay, since we have degree 8, we do have 8 zeros, but they're all imaginary. Okay, they're imaginary. So to find those, you'd have to use advanced techniques, some trigonometry, and so forth. If you actually graph this, okay, other ways to find zeros, as I've done some videos with using calculator. Okay, you could actually sketch the graph. If the graph is strictly above the x-axis, in other words, it has no x-intercepts, or if it's strictly below the x-axis with no x-intercepts, in other words, the graph doesn't cross the x-axis, then that tells you there's no real solution. Okay, so again, this is Descartes' Rule of Signs, which gives you the possible real positive zeros or the possible negative real zeros that a polynomial can have. And it just makes it a little bit easier to solve the problem if you're having something like finding the zeros or solving a polynomial equation, because once you get one or two zeros, you can go ahead and start factoring the expression and getting the rest of the zeros. Okay, hope this was clear. Let me know if you have any questions, and we'll see you in the next video. Take care.